Okay, thanks for inviting me to give this talk in this cool conference. The title of my talk today will be on the monopole Lefschetz number of finite order diffeomorphism. And this is based on a joint work with Danny Ruberman and Nikolai Saveliev. Okay. In this part one of the talk, I will mainly talk about the statement and of the main result and some idea of proof, and as well as some motivations, the applications to knot theory and the L-space conjecture will be included in the second part of the talk. Okay, in part one, I will first give a quick review of the monopole Floer homology, and then I will define the monopole Lefschetz number of a self-diffeomorphism on three manifold. And then I will state the main theorem, which can be summarized as monopole Lefschetz number plus Forshoff invariant equals Kessler invariant plus signature. And I will motivate this main result from some conjecture in gauge theory that relates some Seiberg-Witten invariant with some Donaldson type invariant. In the end of part one, I will sketch the idea of proof. Okay, let's start. So first, let me give a very quick review of some basic property of the monopole Floer homology. For this talk, we will let sigma be a closed oriented three manifold, and we will assume sigma is a rational homology three sphere, namely the first Betti number of sigma equals 0. Okay. This should be sigma here. The monopole Floer homology of sigma, well, there are three versions of them called HM2, HM from, and HM bar. These are powerful invariant defined by Kramer-Morovka, and for the case of rational homology three spheres, also by Forshoff. Okay. Very roughly speaking, these invariants are defined by a certain chain complex whose generators are solutions of Seiberg-Witten equations on the three manifold. We will just call such solutions to be monopoles, and the differential in this chain complex will be obtained by counting monopoles on this R cross sigma. Okay, and so as you can see, there's three different versions of monopole Floer homology, and when I just use this notation without specifying notions, I just mean the same result hold for all three flavors. Okay, and this it turns out that this monopole Floer homology encodes some really interesting but subtle information about the underlying three manifold. For example, it detects the fiberness, the Thurston norm, and it also tells us some useful information about existence of foliations and so on. Okay. And also note that by the work of Kurt Luhan Lee Taubes, or alternatively calling Gijini Honda and Taubes, now we know that monopole Floer homology is isomorphic to the Higa Floer homology. Okay. And in order to talk about the monopole Lefschetz number, we need to talk about the functionality of a monopole Floer homology. We let sigma 0, sigma 1 be two three manifolds, then cobordism from sigma to 0 to sigma 1 is a pair, W and rho, where W is an oriented four manifold with boundary, and rho, which we call as the boundary parametrization, is a homeomorphism between the disjoint union of sigma 0 and sigma 1 to the boundary of W. Here, negative sigma 1 simply means the orientation reversal of sigma 1. Okay. And by counting solutions of the Seiberg-Witten equation on W, one can define a linear map between these two vector spaces. That's the so-called cobordism induced maps. And this allows us to define the action of a self-diffeomorphism on the monopole Floer homology. So we let F be a self-diffeomorphism on the three manifold sigma, and we can consider the so-called twisted product cobordism. the four manifold is just the product homologism. Zero is just the product for manifold. But now we don't use the most naive boundary parameterization. Instead, we use the identity map on one boundary component and use this diffeomorphism on the other boundary component. Okay, and this twisted product homologism give us a well-defined self-isomorphism going from monopole Floer homology of sigma to itself. And the motivating question is to understand this induced action F star and use it to give some interesting geometric information about the diffeomorphism F. So that would be the motivating question. Okay, then we have this map F star, which we want to understand. Well, unfortunately, it seems very difficult to completely computing F. Okay. So that's usually true for gauge theory. It's quite hard to compute those invariants in a direct way because that involves solving some nonlinear partial differential equation. So a more realistic way, goal is to compute some partial information on F star. In our situation, this will be some Lefschetz number of F star. Okay. Well, think about the Lefschetz fixed point theorem for finite dimensional simplicial complex. This such Lefschetz number, heuristically, it should count some monopoles or solution of the Saveliev equations on the three manifold that are invariant under your diffeomorphism F. Okay? And in order to make this heuristic rigorous, we need to recall the structure of the monopole Floer homology. So let's do that now. Okay, so we will be mostly focused on this version, HM2. Recall that it's actually defined as the direct sum of the corresponding invariant for each spin C structure on sigma. And we also note that for each of this group carries two gradings. One of them is the rational grading, the other one is the ZIMO2 grading. Okay, and we also have a short exact sequence which goes from this specific U module to the monopole Floer homology, and then to the quotient has a name, it's called the reduced monopole Floer homology. Okay. This is a finite dimensional vector space, unlike this. Unlike HM2, HM red is a finite dimensional vector space, and the U action on this on the reduced monopole Floer homology is nilpotent. Okay. And we also recall that the Floer invariant, which is the rational number, is defined as is negative half of the rational grading of the bottom term in this tower part. Okay. And we'll be mainly interested in the normalized monopole Lefschetz number. That means that we take the induced map F star on the reduced monopole Floer homology. We take its Lefschetz number, and then we add this Lefschetz number by the Floer invariant. Okay, and recall that the Lefschetz number of a linear map is simply the trace of the even part minus the trace of the odd part. So we will call this combination as the normalized monopole Lefschetz number. Okay, and so now let me give the statement of the main theorem. To begin with, we consider a self-diffeomorphism on F on a rational homologous three-sphere sigma, and we assume the following conditions. First, F is of finite order. F is a finite order self-diffeomorphism, and second condition is that the quotient space is an integer homologous three-sphere. Okay, in general, if you just take a finite order self-diffeomorphism on a rational homologous three-sphere, you only get a rational homologous three-sphere. But to simplify our discussion, we assume the quotient space is an integer homology sphere. And the third condition will assume that F has some fixed point set, and the fixed point set is connected. And in particular, this will imply that if given not K inside the quotient space Y. Okay. And let me note that condition 2 and 3 are actually inessential. We expect that our result can be generalized to work on a arbitrary finite order diffeomorphism on rational homology 3 spheres. Okay. And so an equivalent description of this setting is that sigma is the n-fold cyclic branch cover of an integer homology 3 sphere Y with branching set and not K. And F is just the covering transformation. Okay. And also note that because this condition 2, there is a unique spin C structure that is on sigma that is preserved by F. Okay. All other spin C structure will be switched by F. Therefore, they do not contribute anything to the Lefschetz number. Okay. And now let me state the main theorem. The main theorem states that the normalized Lefschetz number, which is just the left-hand side of the equality, is a linear combination of the Kessel invariant lambda y, which is some count of SU2 representation of the fundamental group, and this Tristan-Levin signature, or some people call them twisted signature. It's defined as this signature of this expression, where A is the Seifert matrix. Okay. All right, and so in other words, we are able to express this monopole Lefschetz normalize the monopole Lefschetz number in terms of some more classical invariants, including the Kessel invariant and the twisted signature. Okay. Yeah, so before talking about the proof, let me give some motivation about this result. The motivation, our original motivation actually comes from some pure gauge theoretic conjecture in 4-dimensional. Okay. So it's called the so-called lambda SW lambda FO conjecture. To state the conjecture, we let X be a smooth 4 manifold that satisfy the following condition. Basically, X has the same homology of a circle times the 3 sphere, and we also require that the covering space, the infinite covering space has the same homology as S3. So you can basically imagine X as some 4 manifold that cannot be distinguished as the standard S1 cross S3 if you just look at the homology. Okay? And for such manifold, there are 2 gauge theoretic invariants of X. The first one is the Seibert-Witten invariant. This version is defined by Morovka, Ruberman, and Saveliev. Okay, so it's defined as the sum of the monopoles on X. Okay, so one can count the number of Seibert-Witten solutions on X. Well, let give you the classical Seibert-Witten invariant, but in this case, because X has no B2 plus, this monopole count itself won't be will depend on the metric and perturbation. Therefore, it's not a smooth invariant. In order to make it into a smooth invariant, you need to add some index theoretic correction term, which is some other number that also depends on metric and perturbation. And it turns out that if you add them together, these dependence cancel each other, and you actually get a smooth invariant. So that's the Seibert-Witten invariant. And the second invariant is called the Fruta-Alta invariant. It's basically a quarter of the count of anti-self-dual SU2 connections on X. So you can think it as a quarter of the Donaldson invariant in degree 0. Okay. Well, and when Tom, Danny, and Nikolai defined this lambda SW, they actually made a conjecture that for any X that satisfies this homological condition, this lambda SW should actually just be negative lambda FO. And well, if you look at this conjecture, the left-hand side is some invariant coming from Seibel-Witten theory, while the right-hand side is some invariant that comes from the Donaldson theory. So you should think it as some kind of Witten's conjecture for homology S1 cross S3. Okay. All right. And so let's specify this conjecture to the case of mapping tori. So we let F be a finite order diffeomorphism, which makes sigma into an n-fold branch cover of integral homology three sphere. Okay. And now we can form the mapping torus. Namely, we take the product of 0, 1 with sigma and we glue the two boundary components using the diffeomorphism F. That will give us a manifold that satisfies the homological condition previously mentioned. And we actually have a splitting theorem that tells us that whenever you form such kind of mapping torus, the Seibel-Witten invariant will always just be negative the normalized the normalized monopole Lefschetz number. And so our main theorem can be restated as that for such mapping torus, the negative 1 times the Seibel-Witten invariant actually equals this linear combination between the Kessler invariant and the Tristan-Levin signature. And we and actually this theorem was also independently proved by Lanterma. So he is a student of Danny, and Lanter's proof was quite different from us. He developed a whole set of surgery formula that allows him to compute the Seibel-Witten invariant for such mapping torus directly. And actually, Lanter's result is slightly more general than ours. Okay. And if we combine this computation with earlier work of Danny and Nikolai, which computes the fruta-alta part of this mapping torus, then one can actually confirm this lambda SW lambda FO conjecture for mapping torus of any finite order semi-free action on integer homology three spheres. And actually, that's the original motivation with that lead us to the main result. Okay, so let me end the first part by talking a little bit about the idea of proof. I don't want to make this talk too technical, so let me just briefly mention the idea. Okay. So as I said, we just need to compute the Seibel-Witten invariant of this mapping torus. And recall that it's defined, this Seibel-Witten invariant is defined as the sum of the monopole count on the mapping torus plus some index theoretic correction term. Okay, and the first observation is that this XF has a circle action. And the quotient, if you quotient out this circle action, you will get a three-dimensional orbifold. We denote it by YO. Topologically, YO is just the same as the three-manifold Y. But now, because the S1 action is not free, when you take quotient, you will introduce some singular set. And actually, in this case, the singular set is exactly the branching loci. So it's the not K, and it's actually conical. It's actually a cone, and the cone angle is 2 pi over n. Okay. And note that there is a result by Baldrige, which states that all monopoles on this mapping tori are actually invariant under this circle action. As a result, we can also define lambda SW as the monopole counts on this three orbifold plus some correction term. The advantage of this new definition is that now we can continuously change the cone angle from 2 pi over n to 2 pi. And well, both terms in this formula will change during this process. However, we are still able to analyze the change of each term in this formula. The change of the monopole count is controlled by some phenomenon called wall crossing. So basically, that means an irreducible self-Witten solution can either burst or dash from a reducible one. And this index theoretic correction term can be controlled by some spectral flow of the Dirac operator and signature operator. Okay. Anyway, so we were able to relate this lambda SW to some invariant for sigma equals 2 pi. And in this case, when sigma is deformed to 2 pi, these three orbifolds just become the smooth manifold Y. And then we apply the following result due to Yuhan Li and Wei-Ning Chen. So this result states that the classical Kessel invariant for three manifold can be recovered by some monopole count plus some index theoretic correction term. And that finishes the proof. And that's the end of my part 1.